Welcome to the deep dive. Ready to explore math logic and graph theory today?
Sounds a bit intimidating, right?
Maybe, but we're going to make it fun. We've got some cool stuff from a graph theory lecture series, and
We'll break it down, make it clear, and maybe even blow your mind a little.
exactly.
You might be surprised how much graph theory is in our everyday lives.
Really? Like what?
Well, think of it like a code that helps us understand connections,
Oh, okay.
like in social networks or even the way the internet is structured.
Okay, I'm starting to see it, but let's back up a sec. When we talk about graphs, what are we really talking about?
Picture a connect the dots, but with vertices instead of dots.
Vertices, huh?
Yeah. And those lines connecting them, those are the edges.
So it's not just lines and dots, it's about what they represent.
Exactly. And the cool thing is, we can use this simple setup to show all sorts of real-world connections.
I see.
Like in a social network, people are the vertices and friendships are the edges.
So like, if I have a ton of friends online, my vertex would have loads of edges.
Bingo. And that brings us to degree. Basically, it's the number of edges connected to a vertex.
So more friends, higher degree.
You got it.
That makes sense.
It's not just for social media, though. Imagine a map. Cities are vertices, roads are edges.
So a city with tons of roads has a high degree.
Exactly.
So we've got vertices, edges, and degrees. What else should we know?
Well, there's this cool thing called directed and undirected graphs. It's like the difference between a one-way and a two-way street.
Okay.
In an undirected graph, the connection goes both ways, like friendship.
Right.
But in a directed graph, it only goes one way, like following someone on Twitter who doesn't follow you back.
Oh, so like the edges have an arrow pointing in one direction.
Exactly. And this difference is super important because it helps us show all kinds of relationships.
Now, you mentioned something called the handshake lemma before.
Oh, right.
It sounds a bit weird for graph theory.
It's not really about handshakes, but it helps to think about it that way.
Yeah.
Imagine a party, right?
Yeah.
Each handshake connects two people. And in graph theory, those connections are edges between vertices.
So the handshakes are like edges.
Precisely. The handshake lemma says that if you add up all the handshakes everyone makes, it'll be twice the number of handshakes that actually happen.
Well, yeah, because each handshake involves two people.
Exactly. And this applies to graphs too. The sum of degrees in an undirected graph is always twice the number of edges. There's actually a proof for this using a clever trick with a new graph to show the relationships.
Sounds complicated.
It is a bit. Maybe we'll dive deeper into that another time.
Yeah, maybe.
But it shows how even simple ideas in graph theory have deep math connections.
I see that. Okay, so we've got the basics down. Graphs, vertices, edges, degrees, and this handshake lemma thing. Where do we go from here?
Well, now that we know the pieces, let's talk about moving around within a graph. Imagine exploring a city, walking along the streets, or like tracing a family tree. That's kind of what walks, paths, and cycles are all about in graph theory.
So it's like understanding the different routes you can take in a network.
Exactly. A walk is like wandering around, maybe repeating edges or vertices. A path is more specific, no repeating edges.
Like following directions.
Right. And then there are cycles. They're like round trips. Closed paths that start and end at the same vertex.
Like walking a loop in the park, ending up back where you started.
Exactly. And just like paths, there are different kinds of cycles. A simple cycle doesn't let you repeat vertices, except the start and end, of course.
So no detours.
Right. And fun fact, a cycle has to have at least 3 edges.
Why is that?
Well, think about it. One edge, you're just going back and forth. 2 edges, you're back where you started, but you repeated an edge. So you need at least 3 to make that loop without repeating.
That makes sense. So we can move around in a graph in different ways. What else can we do with these graphs?
Well, sometimes you want to focus on a smaller part of a graph, like zooming in on a part of a map or looking at a group of friends on a social network. That's where subgraphs come in.
Like taking a smaller snapshot.
Exactly. And there are different types. An induced subgraph takes some vertices and keeps all the edges between them from the original graph.
So like taking a group of friends and preserving their relationships within that group.
Precisely. And you can also do things like removing a vertex or an edge, like someone leaving a social network or a road closing on a map.
Okay, so graph theory can show these changes.
Yeah, and it brings up another idea, connectedness. How do we know if we can get from one vertex to another?
Like figuring out if you're connected to someone on social media through a chain of friends.
Exactly. In graph theory, an undirected graph is connected if there's a path between any 2 vertices.
Like checking if there's a route on a map.
Right. If a graph isn't connected, it's got separate islands. We call those components.
Like islands and continents.
You got it.
Okay, this is getting really interesting. You mentioned changes to a graph. What happens when you add or remove edges?
Well, that's where the addition and removal principles come in. It's like building or taking apart a network. Adding an edge either connects two islands or creates a new cycle. Removing an edge does the opposite. It either splits something into two or removes a cycle.
So like building or demolishing a bridge.
Exactly. This helps us see how the graph changes when we mess with its structure.
This is fascinating, but it makes me wonder, what about graphs that are connected but don't have any cycles?
Ah, you're thinking about trees. They're connected and have no cycles.
Makes sense, like a family tree but for data.
Exactly. Trees are used for things like file systems on computers or relationships in programming.
So no cycles, just branches connecting everything.
Right. And get this, there are several ways to define a tree, all meaning the same thing.
Wait, different definitions for the same thing? How does that work?
Think about describing a square. You could say it has 4 equal sides and right angles, or a rectangle with equal sides. Both are right, just different ways to say it.
So it's not the words, it's the concept.
Yeah. The source actually gives 4 definitions, all meaning the same thing. Shows the power of math logic, right?
Yeah, I see that. What are the definitions, though?
So first, a tree is a connected graph with no cycles. Second, it's a graph with no cycles. But if you add one edge, boom, you get a cycle. Third, it's a connected graph, but remove any edge and it splits. Lastly, any 2 vertices in a tree are connected by exactly one path.
Wow. It's amazing how math can capture complex ideas so precisely.
It is, right? And these definitions lead to cool theorems. One says that to connect vertices in a tree, you need 1 edges.
So 10 vertices need 9 edges.
Exactly. It's a basic rule of trees, the most efficient way to connect things without cycles.
Wow, trees are cooler than I thought.
They are super important in graph theory and used all over the place.
Okay, we've gotten a good overview of the basics here. Are there any types of graphs that are extra interesting or useful?
Definitely. One that pops up all the time is a bipartite graph. Imagine dividing people into groups like cat people and dog people, or early birds versus night owls.
Like sorting them into teams?
Yeah. A bipartite graph is where you divide vertices into 2 groups, and edges only connect vertices from different groups.
So a cat person and a dog person could be connected, but not 2 cat people.
Exactly. It's everywhere. Think about matching jobs to applicants, students to courses, even dating apps.
Wow, I see that. Can you tell if a graph is bipartite just by looking at it?
Yep. A graph is bipartite only if all its cycles have an even length.
Hold on, what does that mean?
Back to cat and dog people. In a cycle, you got to alternate between them as you go around.
So you need an even number of steps to get back to the start.
Right. If it was odd, you'd end up in the wrong group. There's a proof for this too. Maybe we'll save that for later.
Okay, maybe. But this dividing vertices thing makes me think, what if you draw a graph on paper without any lines crossing? Can you always do that?
Great question. That's what planar graphs are all about. They can be drawn on a flat surface without any edges crossing.
Like a map or a circuit diagram.
Perfect examples. And they have some interesting properties. One is Euler's formula, which links the number of vertices, edges, and faces in a planar graph.
Wait, faces. What are those?
When you draw a planar graph, the edges divide the paper into regions. We call those faces.
So on a map, faces would be countries or states.
You got it. Euler's formula says for any connected planar graph, vertices plus faces minus edges always equals 2.
That's cool. Is it hard to prove?
It uses induction and looks at how removing an edge affects the faces, but we've had enough proofs for today.
Probably right. Are there graphs that aren't planar, though? Like, can you always rearrange the vertices to avoid crossings?
Nope. Some graphs are just non-planar no matter what. One is called K5, a complete graph with 5 vertices, where every vertex is connected to every other one.
Complete graph. Remind me what that is.
It means every vertex is connected to every other vertex by an edge.
Okay, I can picture that. So why is K5 not planar?
There's a rule for planar graphs. With at least 3 vertices, edges must be less than or equal to 3 times the vertices minus 6.
So there's a limit on connections in a planar graph.
Exactly. And K5 breaks that rule. It's got too many edges to be drawn flat without crossings.
So it's too dense to be planar.
Yeah, you could say that. And another non-planar one is K3$3. That's a complete bipartite graph with 3 vertices in each group.
Ah, like the cat and dog people, but 3 of each.
Exactly. It also has too many edges to be planar. Bipartite planar graphs have an even stricter limit.
So these non-planar graphs are like rebels, always breaking the rules.
That's a good way to put it. They show us that not every graph can be drawn the same way.
Well, my brain's full of graph theory for one day. We've covered so much, it's amazing how these abstract concepts can be used for real problems.
It's really cool, isn't it?
Yeah. I think we'll have to continue this deep dive next time.
Definitely. There's always more to learn.
For now, we hope you're starting to see the power of graph theory and how this math idea is connected to so much in our world.
It's amazing how these simple ideas can be so powerful, right?
Yeah, it's really making me think differently about networks and connections.
Exactly. And speaking of connections, I think it's a good time to talk about a related concept, homeomorphs.
Homeomorphs.
Yeah.
Okay, that sounds intimidating.
It's not as scary as it sounds.
Yeah.
Imagine you have a graph and you want to make it a bit more complex by adding some extra vertices along the edges.
Like adding more stops on a road trip.
Yeah, exactly. You're basically subdividing the edges by adding these extra vertices.
Okay, I can picture that.
The new graph with the extra vertices is called a homeomorph of the original graph. And the interesting thing is that these homeomorphs often keep some of the same properties as the original graph, especially when it comes to being planar or not.
So even if we add these extra vertices, the graph might still not be planar.
Right. There's this theorem, Kuratowski's theorem, that says if a graph has a copy of a homeomorph of K5 or K33 as a subgraph, it's definitely not planar. Remember those non-planar graphs we talked about?
Yeah, the ones that are too dense to be drawn flat without crossings.
Exactly. Kuratowski's theorem tells us that even if we try to hide those non-planar graphs by adding extra vertices, we can't change their fundamental nature.
So they're like the troublemakers of the graph world.
That's a good way to put it. And this theorem is important for things like designing circuits, where you really want to avoid those crossings.
I see, that makes sense. But sticking with planar graphs for a minute, if a graph is planar, does that mean all the vertices have to have a low degree? Like, could you have a planar graph where every vertex has a degree of, say, 100?
Nope. It's a cool fact that every planar graph has to have at least one vertex with a degree of 5 or less.
Really? So no matter how hard you try, you can't pack a ton of connections into every vertex and still keep it planar.
Exactly. There's actually a proof for this using the average degree of vertices in a planar graph.
That's wild. So even in the most connected planar graphs, there's always at least one vertex that's a bit more chill.
That's a great way to think about it. It's a good reminder that there are limits to how much you can connect things in a planar graph. But speaking of connections, there's another aspect of graph theory we should explore. Special kinds of paths and cycles that go through all the edges or all the vertices.
Okay, I'm listening. What kind of paths and cycles are we talking about?
Let's start with Eulerian paths and cycles. An Eulerian path is a path that visits every edge of the graph exactly once, no repeats. It's like taking a walk through the graph and making sure you go down every street exactly once.
Sounds like a fun puzzle. Is it always possible to do that in a graph?
Not always, but there's a theorem, Euler's theorem, that tells us exactly when it's possible. For a connected graph, it says that a graph has an Eulerian cycle if and only if every vertex has an even degree.
So every vertex has to have an even number of edges connected to it. Why is that?
Think of it like this. Each time you enter a vertex along one edge, you have to leave it along a different edge. To use up all the edges connected to a vertex, you need to enter and exit an even number of times. If a vertex had an odd degree, you'd either get stuck there or have to repeat an edge, which isn't allowed.
That makes sense. It's like making sure you have an exit every time you enter a room.
Exactly. Now, what about Eulerian paths that aren't cycles? That means you don't end up back where you started. A connected graph has an Eulerian path if and only if there are either 0 or 2 vertices with odd degrees.
So either all vertices have an even degree or there are exactly 2 with an odd degree.
Right. Think of it this way. If you have an Eulerian path that's not a cycle, you're starting at one vertex and ending at a different one. Those starting and ending vertices would be the ones with odd degrees because they have one edge that's not paired with another.
I get it. Those 2 odd vertices are like the start and finish line of our walk.
That's a great way to put it. Euler's theorem is really useful because it gives us an easy way to tell if a graph has these special paths or cycles just by looking at the degrees of the vertices.
That's really neat. And I bet these Eulerian paths and cycles are used in lots of real-world planning, right?
Absolutely. They're used in things like route planning, optimizing networks, and even figuring out the best way to sequence DNA.
Wow. So many practical uses. It makes me wonder, what if we want to visit every vertex in a graph exactly once instead of every edge? Is there a name for that kind of path or cycle?
Those are called Hamiltonian paths and cycles. A Hamiltonian path visits each vertex exactly once, and a Hamiltonian cycle does the same but starts and ends at the same vertex, forming a loop.
That sounds like the traveling salesperson problem where you have to find the shortest route to visit every city once.
That's a perfect example. And unlike Eulerian paths and cycles, there's no easy way to tell if a graph has a Hamiltonian path or cycle just by looking at it.
Really? How come?
Finding a Hamiltonian path is a much harder problem for computers to solve. It's what we call an NP-complete problem, which means that if we could find a quick way to solve it, we could solve a whole bunch of other really hard problems as well.
So it's like a key that unlocks a bunch of other puzzles.
Exactly. And because it's so tricky, there's no simple theorem like Euler's theorem that gives us a clear condition for when they exist.
That's too bad. But are there any theorems at all that give us hints about Hamiltonian paths?
There are a few. One is called Orr's theorem. It says that if a graph is well connected enough, it has to have a Hamiltonian cycle.
So if the graph has enough connections, it's guaranteed to have a Hamiltonian cycle.
Exactly. There's also a version of Orr's theorem for Hamiltonian paths. But even with these theorems, finding Hamiltonian paths is usually still really tough.
This is getting pretty complex. But before we move on, can you give me an example of how these Hamiltonian paths are used in the real world?
Of course. Imagine you're planning a delivery route. You have a bunch of stops to make, and you want to find the most efficient route that visits each stop exactly once before returning to the starting point.
That sounds just like a Hamiltonian cycle.
You got it. Hamiltonian paths and cycles are used in logistics, transportation, and even DNA sequencing to solve these kinds of optimization problems.
It's amazing how this seemingly abstract math idea is so useful in so many different fields.
It really shows how powerful math is for understanding and solving real-world problems. And as we keep digging into graph theory, I'm sure we'll find even more fascinating connections.
It really is amazing to see the connections between these abstract math ideas and real-world problems.
It's what makes graph theory so fascinating, right? It's not just about equations and theorems, it's about understanding the structure of the world around us.
You know, thinking about all the different types of graphs we've talked about, I have a question. We've covered trees, which are connected and have no cycles, and we've talked about bipartite graphs, where you can split the vertices into two groups. But can a graph be both a tree and bipartite?
Ooh, that's a great question. It's like asking if something can be both a bird and a mammal. And the answer is yes. There are graphs that are both trees and bipartite.
Okay, I'm curious. What makes these graphs so special?
Well, let's think about what it means for a graph to be both. As a tree, it has to be connected and have no cycles. As a bipartite graph, we need to be able to divide its vertices into two groups, let's say A and B, so that edges only connect vertices from different groups.
So it's like a connected graph with no cycles, where every edge goes between group A and group B.
Exactly. Imagine starting with a vertex in group A. It can have connections to lots of vertices in group B, but none of those vertices in group B can be connected to each other.
Why not?
Because then we'd have a cycle. And trees can't have cycles.
Oh, right. So the connections had to branch out from that initial vertex in group A, but they can't loop back.
You got it. And that pattern continues as the graph grows. Every vertex in group A can connect to multiple vertices in group B, but those B vertices can't connect to each other or back to that first A vertex.
It's like a tree with roots spreading out, but the roots can't touch.
That's a great way to visualize it. And that branching structure makes these tripartite graphs really useful. They're great for showing hierarchical relationships between two different types of things.
Can you give me a real-world example?
Sure. Imagine a website that connects freelance writers with clients. The writers would be in group A, clients in group B.
And the edges would be the connections between writers and clients who've worked together.
Right. Since it's a tree, there's only one path between any writer and any client. You could see how they're connected through past projects.
That's cool, like a family tree, but for professional connections.
Exactly. And because it's bipartite, it keeps those two groups, writers and clients, separate, with connections only between them.
So this mix of tree and bipartite features is really powerful for certain data.
Definitely. It's a perfect example of how graph theory can be used to solve real-world problems.
Well, this deep dive into graph theory has been amazing. We started with the basics, and now we're talking about all these complex ideas.
It's been a fun journey.
And for everyone listening, we hope you've learned something new and are starting to see the beauty and power of graph theory. It's all around us, shaping the networks that make up our world.
And who knows, maybe you'll even start seeing graphs everywhere you look.
Until next time, keep exploring.